Good luck reading it.
Why?
Oh, remember later, I got married.
That's the LED. I've been
You should do that.
Our Spanish teacher loves you. What are you? Bro, I talk to her every Friday. That's because you.
Okay, if you can turn to page 19 in your
Check it
packet.
out, bro. Check it out, bro. It's Kyrgyzstan. Yeah, but it's like
So
right at Xbox.
we still have AP practice as far as FRQs that we want to review in preparation for the AP exam, at least the AB content. But this is basically our final new topic for this semester, our final AB new topic. And then after this, after you get done with this unit, there's still one or two FRQ type problems you haven't seen, but they're basically just ways of involving integrals through called rate in, rate out problems. So we'll definitely look at those and get practice with AB FRQs after we get through with this unit. Okay, so we're talking about cross section. So cross section is the shape that results if we were to cut the object in half and look at the resulting shape sideways. So this method and washer method, we're always rotating around an axis, and that rotation is always creating a circle. So this method and washer method problems are all going to give us circular cross sections, right? If we were to slice the object and open it up, we're always going to see these circular shapes. So that's why there's always pi involved, since we're adding areas of circular shapes over the course of the interval. So your volume formula for disk and washer method always has pi involved. So that rotation is what's causing that circular shape. But today we're talking about what if we were building certain shapes not out of rotation, but on a base, and we're building different cross sections from that base. So what if we were to build squares, add infinite numbers of squares on top of a base, or add infinite numbers of triangles, or rectangles, or semicircles? There's not going to be any names for these shapes. And we're not going to have to worry about recognizing them in terms of visualizing them. We should have to be able to get enough information to put into the formula and then spit out the volume. Okay. So here is, this diagram is not very clear, but let's say we have a shaded region that is represented in the first quadrant here. Okay. And if we were to add infinite numbers of differently shaped squares on top of this base, it'll end up looking something like this, where we're adding these infinitely thin slices of squares. And as we get closer towards the y-axis, that base will get longer, which means that the height will get larger, because if we're dealing with squares, our length and width will be the same height. So we're getting these odd-shaped objects. In the textbook, I can also show you some of these objects here. This is what an object with a triangle cross-section would look like. This could be an object of what a square cross section could look like. Textbook shows if I have a cross section that looks like a circle, but my base that's shaped like a circle, but my cross section is a triangle, then we get something shaped like that. This is another cross section that is squares. Okay, but again, no need to. Here's one that involves squares. We don't have to worry about drawing them. We're just getting enough information to plug into the volume formula, and really that's it. Okay. So let's, there's a series of formulas as well that we're going to be responsible for, but there's going to be some nice patterns that I'll talk about later where we really have to worry about the coefficient as we're memorizing these formulas. But we'll start with, let's start with example 1, and then I can revisit the formulas as we talk about it. So example 1, it says find the volume of the solid of the base bounded by the curve y equals root minus 1x root 1 minus x squared, y equals 0, and x equals 0 in the first quadrant. So we're going to find the shaded region. We're going to find the bounds. We're going to find the orientation that we're dealing with. Are we dealing with a vertical base or a horizontal base? So with area, I would say rectangles. For cross section, for this method, Washer method, I would use the word radius. But for these cross section problems, I'm going to use the word base. But essentially, it's going to be some rectangular representation of our of what we need. Okay, so we're basically doing this problem here, but I'm going to draw this not from a 3-dimensional perspective, but from our normal 2-dimensional perspective. So here's square root of 1 minus x squared. It's going to look like a quarter circle here. And it's bounded by y equals 0 and x equals 0. So it's going to be bounded in the first quadrant. Now, the cross sections are squares. So we're going to use the square formula. But the first thing we want to do is we got to make sure that we understand which direction are we building our squares. And we want to build it parallel to the y-axis. So which direction is that? Is that vertical or is that horizontal? Vertical. Okay. So you're always going to be told exactly how to, in which orientation to draw your base length. Okay. We don't have to worry about, okay, the axis is vertical, so my radius is going to be horizontal. They're going to tell you exactly how to build it. Okay. So parallel to y-axis is vertical. So this will be a representative base length of a square. We can kind of imagine that this is sitting on top of a paper, and then we're building these squares that's gonna come out of the paper. Okay, and the visual representation will be this, but we're not going to have to draw that. We just have to be able to find enough information to do it. So we have a vertical base, so that's going to be a little bit easier. We just do top minus bottom, just like how we did with the radius. So our base length is top minus bottom. What's the top of my base length sitting on? Yeah, square root of 1 minus x squared minus, what's the bottom sitting on? 0. Okay, so that's just going to be root 1 minus x squared. Okay, and then my bounds, because everything's in terms of x, we're going to use the top minus bottom vertical base formula. So our bounds is also in terms of x. So we're basically adding these infinitely thin squares from one end to the other. So what are our bounds going to be from 0 to, what's the x-intercept here? Just 1, right? So if I set root 1 minus x squared equal to 0, that's just going to be equal to 1. So my bound is going to be from 0 to 1. Let's build our area. Our area it's a square, so it's base squared. So we have our base. Let's square our base. So base square, so root 1 minus x squared squared. Now that we have our area, we're going to accumulate that area over the interval over the course of our intervals. So our volume formula is just whatever area that we found, whether it's a square or triangle or a semicircle, we're just going to surround that with the integral notation in dx. Okay. So after we find our area, we're just going to surround it, give it that third dimension that it needs. So v is equal to, again, this one, most of your cross section will not have pi because there's no rotation going on unless it's a semicircle. So we have to keep reminding ourselves, okay, there's no pi in front, even though we've been used to it, getting used to it with disk and washer method. There's no rotation here. So the definite integral from 0 to 1, square root of 1 minus x squared, which can just cancel out to be just 1 minus x squared. And then we just enter this in our calculator and find our volume. So math 9, from 0 to 1, you can have the square root and the square cancel each other out. And then we're just left with 2/3. There's no pi involved. There's no rotation. So it's just going to be units cubed. You can remove that. Let's go to page 20. Find the volume of the solid bounded by the curve y equals x squared and the line y equals 4. So let's go ahead and find our shaded region first. Okay, now we want to build isosceles right triangles that sits on top of this base. But it's going to be isosceles right triangle whose hypotenuse lie on the base. So there's a very specific formula for that. But the first thing we want to do is, which orientation are we dealing with here? Which direction do we want to draw our base length? Parallel to the x-axis. Which is that, vertical or horizontal? Horizontal. Okay, so we want to extend our horizontal base from one end to the other. So imagine this is sitting on your paper and you're building these triangles that's going to come out of the page. Whatever that shape looks like. Now we see a horizontal base, which means there's more work ahead of us, right? We can't use the equation that's given to us. We have to rearrange it in the proper form. So we need to rewrite our equation here. So if we solve for x, what is that going to turn into? X equals what?
Root y.
Okay, a little bit more. X equals.
Oh, 2. Oh, right, no, never mind.
What happens if I take the square root of both sides? Plus or minus, right? So these are two separate equations, plus or minus root y. So there is a positive root y. Which is of that. Y. And then we also have x equals negative root y. That's going to be over here. So there we have our two separate equations that we're going to be using to build our do right minus left. Okay, so our bounds. We're stacking these triangles from lowest to highest y value. What are our bounds going to be? Lowest y value is 0. Highest y value is 4. Okay. Let's build our base length. Right minus left. Right endpoint of my base length is sitting on the positive root y. Minus left endpoint is sitting on the negative root y. It's going to combine to be what? 2 root y. So once we have our base, let's build our area. Our area that we want is isosceles right triangle with hypotenuse on the base. It's going to be 1/4 base squared. So 1/4 base squared. Multiply that out to clean that up. We get 4y over 4, which is equal to y. And once we find our area, then we're just surrounding it with the integral and dy notation. So our volume is just the integral from, you said it, from 0 to 4, y dy. We've already cleaned all this up. Okay. Plug in the calculator or work it out by hand. This will end up giving us 8 cubic units. Number 3 should be easy because we're dealing with the same graph. But look at the wording here, though. We want to build semicircle, so different shape. Perpendicular to the y-axis. Which orientation is that? Horizontal or vertical? Horizontal. So notice how there are different ways that they can problem can indicate something is horizontal. All right, so we don't want to just look at the word parallel or just look at the x or y axis and assume that it is, you know, one orientation or the other. Make sure that you're paying attention to both sets of words and then convincing yourself that it's either one or the other, that you're not that you're paying close attention to the wording of it, because you know there's 2 ways to say horizontal and there's 2 ways to say vertical. So perpendicular to the y-axis is still going to be horizontal. So a lot of information we can just carry over, right? Because our bounds will still be the same. Our base will still be the same. But our area is a little bit different. Our area is semicircle. So semicircle formula is pi over 8 base squared. Which if I clean this up, I get 4 times y. 4 over 8 is 1/2. So 1/2 pi y. I can just surround my area with integral notation and dy. Again, leave pi out of your calculator. You want to do it this way. And that will give us 4 pi cubic units in your calculator, or you can work it out by hand. All right, example 4. Let region R be the area enclosed by the function natural log of x and 1/2 x minus 1. The natural log of x is going to be the curve. The 1/2 x minus 1 is a linear graph. Region R is the base of a solid. That each cross section perpendicular to the x-axis. Oh, yours is the one on top. Yeah, I think that's yours. Okay, which direction is this? Perpendicular to the x-axis.
Vertical.
Vertical. Okay, so we can draw one representative base. We know vertical is the easier one. We know that we don't have to worry about rearranging the equations. The equations are good to go. Our bounds will come from the intersection. So take the time to graph this in your calculator. We need to find these intersections, and then the left and right bound will be our, or left and right intersections will be our lower and upper bound. I'm going to put a box around that region so I can have an easier time. So I did zoom box, and I'm just moving my cursor to where I think I want the upper left corner of my box to be. Hit enter, and then use your arrows to draw your box. Don't hit enter again until you have the box in front of you. Okay, so now I'm going to use my intersect feature, second trace 5. I'm going to pick a point close to my left intersection, but don't put your cursor on the intersection. Put it near. The calculator just needs to know that that you're looking for the intersection between these two curves. Hit enter again. It should find that intersection for you. So 0.463 or 0.464. And then we'll try again. Second trace intersect. Now I'll pick a point close to the right intersection so the calculator knows which one to look. Hit enter, enter, enter a third time. It'll find that intersection on the right. 5.356 or 5.357. Oops, 5. We start off with our base. Base is top minus bottom. Top is sitting on the curve, which is that natural log of x. Minus this one, we do need a set of parentheses, otherwise we're going to forget to distribute. The bottom is the 1/2 x minus 1, which if I clean this up, will just be natural log of x minus 1/2 x plus 1. Now that we have our base, let's move into decide what shape do we want to build on top of this base. We want to build isosceles right triangle with a leg on the base. So isosceles right triangle with leg on the base is 1/2 base squared. Now that you have your area, you're just putting the next stage is getting into the third dimension. So you can just put your integral notation around it. and then the rest can just be your calculator entry. Right, any questions? Let me talk about these area formulas for cross sections. I know it seems intimidating to ask you to, or it's intimidating to think about having to memorize all these formulas, but what do you notice is common between majority, if not all, these cross-section formulas? They all have what?
Base squared.
They all have base squared, right? And you already know the area of a square is base squared. Everything is just going to be built off of that, except for rectangle. Rectangle is a base times height. If it's a rectangle, the height will be will be described to you in the problem. We'll look at some problems where the height is described, but we know rectangle is base times height. We know square is base squared, and everything else we just have to worry about memorizing the coefficient in front of the base square. So isosceles right triangle with leg on the base is a 1/2 base squared. Isosceles right triangle with hypotenuse on the base is a 1/4 base squared. Equilateral triangle is √3/4 base squared, and a semicircle is power over 8 base squared. So yeah, most of the formulas are base squared. Just have to worry about memorizing the coefficients. And then a common mistake that students make with cross section is misreading the description and getting the orientation incorrect. So let me just show you the 4 orientations and make sure that we understand there are multiple ways of saying horizontal or vertical. And let's just have us think through these here. So parallel to the x-axis, what does that mean? Horizontal or vertical? Horizontal. Right. Perpendicular to the x-axis.
Vertical.
That's vertical. Parallel to the y-axis.
Vertical.
Vertical. Perpendicular to the y-axis. Okay, so just be careful when you're reading the problem that don't just assume, oh, I see the word parallel, it's got to be, you know, this direction. Oh, I see y-axis, it must be this direction, right? Pay attention to both words and put it together and make sure that you're making the correct orientation so it doesn't throw off your entire problem. Like, that's basically it with cross section. Okay, let's look at some example FRQs. We'll try to get through one. So let's go to page 21. You need your calculator. So we're gonna have to put this in our calculator and find those intersections. So it says let R be the region bounded by the graph y equals e to the 2x minus x squared. That's gonna be this curve here. We have the horizontal line y equals 2. Let S be the region bounded by the graph of e to the 2x minus x squared. Find the area of R. So area of R, we can do top minus bottom. We just have to graph this and find those intersections as our bounds. Okay, try that. You may have to zoom in since it may be a little small with the standard window. If you want, you can also draw a box around where you want to focus in on. Second trace, intersect. Move close to your intercepts. I got 0.446. And 1.554. You just do top minus bottom. We're just doing area here, so no rotation, no this method, no washer method, just top minus bottom. The top of my rectangle is sitting on the curve. The bottom is sitting on the y equals 2. So either 2x minus x squared minus 2. So math 9. So no square, no pi. It's just integral dx. Integral of my top minus bottom dx. Part B, find the area of S. So there's two ways of doing this. One way is we can maybe think of this as, well, I have region S, region R already. So we can find the area of this region, find the area of the rectangle, find the area of that portion there. So that's doable. We can definitely think of it as 3 separate regions and then add them together. What's another way of finding area S?
I think the area like R plus S, subtracting R.
Yeah, we just find the area of that and then subtract out the part A that we got, and that's another way. Maybe that's a little bit faster, but it does require, seeing it from that perspective. So I think that's the easier one, but it does require some perspective to see that. Okay, so try part B. We do need to find the intersections. Well, this one, yeah, confirmed that that's 0. But we do need to find that intersection as our bounds for the whole region R plus S. So we find the whole region R plus S and we subtract this out. And what's left over is the area of region S. Okay, let's end with part C. We're going to rotate region R about the line for y equals 1. So there's a gap. So we can expect washer method out of this process. So we're just going to set it up. We're not going to plug in the calculator. All right, part C. The bounds we can reuse for part A since our shaded region is the same as part A. Any questions here? Okay, so check your calendar for your homework. You have some more problems from the textbook as well as AP practice. Tomorrow we'll do a full class period, a quiz review, and then we'll spend another day on Monday. But on Friday, I'm going to start our FRQ practice. But we'll have Friday and Monday to review, and I'll also have help sessions. Tomorrow morning and Monday morning. This. Tell me the funds.